Hello everyone. This is chapter 3.4, exponential and logarithmic equations. So what you have in front of you here are the steps to follow to solve equations involving exponents and logarithms here. I suggest kind of taking a moment here, pausing, and kind of letting yourself digest these steps to follow. These are coming straight from our textbook. So if I'm solving for exponential equations, I'm going to use what I know about their inverse, right? That's what we do when we solve equations, is we perform kind of the reverse order of operations using inverse operations in order to isolate a variable. Well, that's what we want to do here. When we're dealing with exponential equations, we want to isolate that exponential expression. And then logarithms are an operation. They are the inverse operation to an exponential. So if I want to unexponentiate something, I'm just going to take the logarithm. Most often we take the log base 10, but on occasion we will also take the natural log. We use our properties of logarithms to rewrite and hopefully simplify and solve for a variable. For logarithmic equations, we basically do the same thing in reverse. If I need to identify a component of a logarithm, I'm going to have to use what I know about exponentials. I want to isolate that logarithm, rewrite that logarithm in exponential form, and make sure that I check to see that any solutions are in our domain. Remember, with logarithms, we do have a domain restriction that all our solutions must be greater than 0. So let's see. We're going to kind of jump around here. You can see we have quite a few equations to work through. Let's see. Yeah, we have quite a bit. I think what we'll do is we'll kind of pick and choose some key ones to identify, and then I'll work out a few that you can kind of take a look at and see, did it work for you? So here, on number 1, I noticed that I have two exponentials. And those bases don't necessarily work well together, but I do know that both 8 and 256 are powers of 2. So I can rewrite this as 2 to the third raised to the x plus 1 equals, now 256 is 2 to the 8th, I believe. So this is going to be 2 to the negative 8th raised to the 3 minus x. That allows us, with a common base, to set those exponents equal to one another. So over here on the left, I would distribute that 3. I would get 3x plus 3, and that must be equal to negative 24 plus 8x. Well, now I just have a simple logarithmic equation to solve. I'm going to say 27 equals 5x, so x will equal 27 over 5. In this case, I recognized that I had common bases that I could rewrite my equation with. That was my first big step. Over on to number 2 here, I have a logarithm. I have the natural log of x minus the natural log of 3. I think in this case, there's a couple ways we could approach it, but I have the same base on both sides. I could write this as the natural log of x equals the natural log of 3. Well, if I'm doing the same thing, taking the natural log of two quantities, x must equal 3. We can slide over to number 3 and see what else happens. Here I have e to the x equals 7. So what I would do here is I have an exponential. That exponential has been isolated. So I'm going to take the natural log of both sides, right? So what's going to happen on the left, the natural log of e to the x is just x. And the natural log of 7 is some number we could evaluate. In this particular problem, we are not using a calculator, so that's as simple as it will get. We can keep working here. Number 4, I have the natural log of 3. The natural log of x equals 3. So kind of in the reverse of what I just did, I'm going to exponentiate each side. In other words, rewrite this with base e to the ln of x and e to the third. Just to rewrite that, I have e raised to the natural log, sorry about that, of x equals e to the third. Well, on the left-hand side, the e and the natural log undo one another. I'm left with simply x. And on the right-hand side, e to the third. You can see a lot of our familiar steps are showing up here. We are working backwards to isolate a variable. So I think I'd like you to try the next few on your own. That's going to be 5 through 8. As we've been doing, I will pause and work these out. I know it'll just feel like a quick second for you all, but I think it definitely is worth pausing and trying these on your own, and then you can kind of watch me talk through them. All right, let's see how those 5 problems went for you. On number 5, I performed a process similar to what we did on number 4. I had log, well, it wasn't stated, but log base 10 of x. So I raised both sides as exponents on to 10. That left me with 10 raised to the log base 10 of x, which is just x, equals 10 to the negative 1. On number 6, this is a very common route to take when solving a logarithmic problem. If we just simply rewrite using what we know about the definition of logarithms and how we can write them as exponentials, we can quickly simplify this logarithm to 3 to the 4th equals x, and we just get to 81. On number 7, we have e raised to 2 different powers, so we can set those powers equal to each other since they are on opposite sides of the same equation. This turns into a quadratic, and since this is an exponential, we really don't have any domain restrictions, so both 4 and negative 1 would work. Moving on to number 8, again, I have a log with the same base on each side. Really need to have that in order to use this technique, right? A log base 3 on both sides means that we're doing the same thing to these 2 expressions, whatever that operation is. So we can set those quantities equal to each other and solve for x. Finally, on number 9, we had one extra step. Notice what I did. I took the left-hand side of my equation and condensed it using my logarithm properties that we saw last lesson. Now that I condense, now I have the log base 6 on both sides. So I can set those quantities equal to each other and solve. So as you can see here, we still are leaning on what we know about inverses to help us solve these whenever we can. If we turn over to page 2, we will see some examples involving our calculator. And again, some of these will be together and some of them you guys will try on your own. So here on example 10, we have 3 times 2 to the x equals 42. And one of the steps we talked about up top, isolate the absolute value, sorry, not the absolute value, isolate the exponential component. So I'm going to divide both sides by 3. So 2 to the x equals 14. Now I can use my change of base property. I can rewrite this as log base 2 of 14 equals x, which if I use my change of base property, x will equal the log of 14 divided by the log of 2. We could use natural log, we could use base 10, either or we could use really any log base. When it's all said and done, our calculator will tell us that our solution here is 3.81. Let's move over to 11. Here we have 5 times 2 times the natural log of x equals 4. So I'm going to try to work towards isolating my logarithmic expression. So I'm going to subtract 5 and divide by 2. So now we can rewrite this as e to the negative 1/2 equals x. Well, I can just plug that right into my calculator, and I'll find that x equals 0.61. Let's look at one more. Here, again, I want to start by isolating my logarithm, so I'm going to divide by 2. So log base 5 of 3x equals 2. Well, from here, I want to rewrite this in exponential form because I can, and I get rid of a logarithm by doing that. So I would raise 5 to the second power, and that would get me 3x. So 25 equals 3x. Well, x will equal 25 over 3. All right, so for these next few, I would like to let you try them on your own. Remember, whenever we're solving a logarithmic or an exponential equation, we want to isolate that log or that exponent so we can convert to another form. If you have multiple logs, you may need to combine them. If you have multiple exponential terms, you may need to use a change of base. But good luck. I will work out these next few problems, and we'll see how they went. All right, let's see how those next 5 problems went. So number 13 was similar to some previous problems. I wanted to isolate that e to the x quantity, so I subtracted 5. I took the natural log of both sides. That kind of unlocks that x as an exponent, right? Natural log is just log based e, so those these two components basically cancel each other out. So we're left with the natural log of 55, or 4.01. Over on 14, a little bit longer process, but the same idea here. I added 4 and divided by 2 to isolate my exponential expression. Then I took the log of both sides. I used the common log base 10. We can use whatever we like. So I took the log of both sides and used my exponent rules, right? This became a coefficient, right? My power rule of logarithms. And then I divided both sides by log of 3. What you'll notice at this point is we've basically created that change of base formula that we saw last unit. From there, I just added 5 and divided by 2. You can see kind of the complicated setup there, but a final answer of 3.42. On number 15, this is one that's a little bit different than what we've seen so far. The trick here is to recognize that our exponents go from 2 to 1 to 0 in the same way that a quadratic might. So we're going to solve this by factoring. Our e to the 2x is the same as e to the x times e to the x. Remember that we add exponents when we multiply common bases. And then I just factored in the adds to multiplies to way. I found that e to the x minus 2 times e to the x minus 1 would equal 0. Well, that means that one of these factors, either of these two factors here must equal 0. So I solved each of those equations independently. On the left, I had to use the natural log of 2. And on the right, I got the result of an exponential was 1, so that exponent must have been 0. Finally, on 16, I had log of 5x plus log of x minus 1 equals 2. So I want to get rid of my logarithm best I can. So in order to do that, I need to condense those two logs into a single log. So I use the product rule. Then I rewrote using my base, right? My base here is 10 raised to an exponent of 2 equals the quantity 5x squared minus 5x, which is just what you see here in green, rewritten in standard form. Well, I set that equation equal to 0. I guess I skipped that step where I divided by 5, but I was left with a quadratic, and I found 2 possible solutions of 5 and negative 4. Now remember, logarithms have a domain restriction. We can't take the log of a non-positive number, so this quantity here, if it were plugged in to either 5x or x minus 1, would result in a negative value in a logarithm, which is not good. So that solution must be extraneous. All right, let's take a look at these compounding interest problems. They want us to know how long will it take $25,000 to grow into $500,000. So I want the current amount to be $500,000, and the initial amount was $25,000. Now, they tell us that we have a 9% interest rate compounded monthly, so we need to use this form, right? So 1 plus 0.09 divided by 12 raised to the 12t. So we're solving this equation for t. So just like we did up above, we want to isolate that exponential expression. We can divide both sides of our equation by 25,000. Really, we're trying to figure out after how long will we have 20 times as much money. So 20 equals, and we can, if this is a calculator problem, we can simplify this quantity here in the parentheses to 1.0075 raised to the 12t. So I can take the log of both sides here. That will unlock my exponent. So log of 20 will equal the log of 1.0075 to the 12t. That allows me to rewrite this as 12t equals the log of 20 divided by the log of 1.0075. That's a change of base, so we can let our calculator do the work there. When it's all said and done, I should find a t-value of 33.4 years. We have one last problem. It is a continuously compounding interest problem. That's where we are going to use this formula here. The current amount is the principal times e raised to the r times t. So we're going to set this up. We are looking to double our money. We're looking for our current amount in our account to be $1,000 after investing $500. That quantity will be multiplied times e. We have a rate of 0.0675, and we multiply that quantity by t. Because this, I'm going to first divide both sides by 500. Really, I'm looking to see after how long will my money double with this given interest rate. I'm going to take the natural log of both sides since I'm working with e, and I will get 0.0675 t equals the natural log of 2. I can divide the natural log of 2 by 0.0675 to get my t value, which I found to be 10.27 years. And we are done.